Welcome to this explainer journey. Today, we're going to try something kind of mind-bending. I want you to imagine zooming into the very fabric of reality. We're going to look way past everything you can see with your naked eye and dive into the absolute fundamental building blocks of the universe.
So, let's just jump right in with a little thought experiment. If you took the world around you and dissected it down to its absolute smallest piece, what do you actually find? I mean, seriously, think about it for a second. If you take a living, breathing human body, or maybe a non-living concrete house, and you just keep breaking them down, cutting them smaller and smaller until you literally can't cut them anymore, what's left at the very end?
Well, let's walk through this zooming in process. You look at a house, right? It's made of walls. Walls are made of bricks. If you zoom into the smallest part of that brick, you're going to find silicate molecules. Zoom into those molecules, and you hit atoms, specifically silicon and oxygen. Now, you might be thinking, hold on, I'm a biologist. Living things are made of cells. True, but cells are made of tissues, organs, and proteins. And what are those proteins made of? Carbon, nitrogen, and oxygen. Atoms. It doesn't matter if you're a mason building a wall or a scientist studying a cell, your starting material is exactly the same. Ultimately, the living and the non-living both boil down to this one exact starting line. We are all, quite literally, just made of atoms.
Chapter 1. Mystery of the Atom.
And that massive realization brings us to the roots of our scientific detective story. You see, long before we had fancy microscopes or particle colliders, we just had pure human deduction. Way back in the 6th century, the Indian philosopher Maharishi Kannada introduced this concept called Parmanu. And around that exact same time over in ancient Greece, philosophers were tossing around the idea of atomos. Now, both of these words translate to the exact same concept, something that is completely indivisible, a particle that you just cannot cut any further. They obviously didn't have the scientific tools to prove it back then, but conceptually, they completely hit the nail on the head.
And you know, this perfectly illustrates how science actually works in the real world. It's like this thrilling, high-stakes baton pass through history. John Dalton kicked off the modern scientific observation in 1808 by arguing that atoms were indivisible. But then, as time went on, every subsequent scientist basically found a flaw in their predecessor's model. From Thomson to Rutherford over to Bohr, and finally to Chadwick. Each of these brilliant minds mentored the next or used the previous guy's data to crack the very next piece of the atomic mystery.
Chapter 2. Thomson and the First Particle.
All right, so let's fast forward a bit to the late 19th century, where this thousands of years old idea of an indivisible atom gets totally shattered. J.J. Thomson was running an experiment with something called a cathode ray tube. To picture this, just imagine a sealed glass tube with almost all the air completely pumped out, so atmospheric gases wouldn't get in the way. When he cranked up a massive electrical voltage to the electrodes inside, he saw this glowing beam shooting from the negative end all the way to the positive end. Now here's the genius part. He put a super lightweight paddle wheel inside the tube, right in the beam's path, and the rays actually made the wheel spin. This was an absolute game changer. It proved these weren't just weird, intangible beams of light, they were physical, moving particles that actually had mass. And since they ran away from the negative side and rushed toward the positive side, they absolutely had to be negatively charged. Just like that, Thomson had discovered the very first subatomic particle, the electron.
Now, since atoms in nature are electrically neutral overall, Thomson knew there just had to be some positive charge in there somewhere to balance out all his shiny new negative electrons. So he proposed what's known as the plum pudding, or the watermelon model. Think of an atom like a watermelon. The red, fleshy pulp is this giant soft sphere of positive charge, and the negative electrons are just sort of embedded inside it, kind of like tiny seeds. But hang on a second. Think about the physics here. Let me ask you, if positive charges heavily repel each other, how on earth does this giant, soft, positive pulp manage to hold itself together without flying apart?
Chapter 3. Rutherford's Gold Foil. Well, that exact watermelon flaw perfectly sets the stage for our next big breakthrough. Thomson's own student, Ernest Rutherford, decides to set up an experiment to test out this watermelon model, and in doing so, he accidentally rewrites chemistry entirely. What Rutherford did was aim a really narrow, high-speed beam of positively charged alpha particles, which are basically just helium atoms stripped of their electrons, and an incredibly thin sheet of gold foil. Based on the watermelon model, they fully expected these heavy particles to just punch right through that soft, positive pulp. And to be fair, most of them did. But a few got deflected at really sharp angles. And then, they got the shock of a lifetime. About 1 in every 12,000 alpha particles bounced straight back, a full 180 degrees.
Rutherford himself later said it was like firing a 15-inch naval artillery shell at a piece of tissue paper and having it bounce right back and hit you. No way, right? This meant the positive charge definitely wasn't some spread-out soft pulp. It was a ridiculously hard, unbelievably dense, positively charged core.
So, the absolutely crucial takeaway here is just the mind-bending scale of what Rutherford discovered. He did the math and calculated that the atom is roughly 100,000 times larger than this new ultra-dense core, which he named the nucleus. To really put that into perspective, imagine you're standing in the middle of a massive football field. Now put a single tiny pea right on the 50-yard line. That pea, that's the nucleus, holding all the positive charge and practically all the mass of the atom. The entire rest of the football field is completely, totally empty space, with incredibly light electrons just zooming around it. Let that sink in. That means you, me, the device you're watching this on, literally everything around us is 99.9999% empty space.
Now, Rutherford pictured these tiny electrons orbiting that dense nucleus, sort of like planets orbiting the sun. It's a really beautiful, intuitive image, but it has a fatal flaw. You see, the classical physics of electromagnetism tells us that if a negatively charged electron is continuously moving in a circle, it's constantly changing direction, which means it is constantly accelerating. And an accelerating charged particle absolutely has to radiate and lose energy. So if it's continuously losing energy, its orbit would shrink. It should mathematically spiral in and crash right into the positive nucleus. If Rutherford was 100% right, all atoms would collapse in a fraction of a second and solid matter just wouldn't exist. Yet, here we are, perfectly stable.
Chapter 4, Bohr Model and Neutron. So how exactly do we fix this collapsing atom problem? Well, we turn to the brilliant solutions provided by Niels Bohr and, just a bit later, James Chadwick. Niels Bohr stepped in and asked a great question. What if electrons don't just move randomly? What if they're locked into specific fixed circular paths, kind of like tracks, called stationary orbits or shells? He labeled them K, L, M, and N as you move outward from the nucleus. Bohr basically laid down a new quantum rule. As long as an electron stays in its assigned lane, it simply does not radiate or lose energy. So no spiraling and no collapsing. He also gave us the mathematical rule for exactly how many electrons can fit in each shell, the 2n² formula. If n is the shell number, you can calculate the exact maximum capacity. The first shell, K, where n is 1, holds 2 times 1 squared, which is exactly 2 electrons. The second shell, L, where n is 2, holds 2 times 2 squared, so 8 electrons. The third, M, holds 18, and the n shell holds 32. Boom! Perfect mathematical order brought back to the atom.
Okay, so now we've got stable, happy electrons, but we still have a huge, glaring problem inside the nucleus itself. If you cram a bunch of positively charged protons together into a tiny, dense core, they should violently repel each other, right? Enter James Chadwick in 1932. He finally uncovered the missing puzzle piece, the neutron. Think of the neutron as the ultimate peacemaker particle. It carries absolutely no electrical charge, 0, and it's actually just a tiny bit heavier than a proton. When you have a cluster of feuding protons desperately trying to push away from one another, neutrons step right in as neutral moderators. They literally increase the physical distance between the protons and provide the strong nuclear binding force that stops the whole nucleus from blowing itself apart. In fact, as atoms get larger and heavier, you actually need a higher ratio of neutrons to protons just to keep the peace.
Let's just pause for a quick second to see how this builds our complete structural picture. We now have our 3 fundamental subatomic particles clearly defined. The electron is negatively charged, zooming around the outside with practically 0 mass. The proton has a positive charge and acts as this heavy anchor right in the center. And the neutron, completely neutral, is actually the heaviest particle of the whole bunch, sitting right alongside the proton to keep that dense core perfectly stable.
Chapter 5, Identity of the Atom. Now that we've mapped out the entire anatomy of the atom, let's talk about how we actually use this information. Like, how do we read, label, and identify these atoms in modern science? To make sure a scientist in the US and a scientist in India are speaking the exact same chemical language, we use the IUPAC standard notation. Honestly, it's brilliantly simple. You take the large chemical symbol of the element and you place 2 numbers next to it. Down at the bottom, as a subscript, is the atomic number. This is purely the number of protons. It dictates the absolute identity of the element. If you change the protons, you literally change the element. Up at the top, as a superscript, is the mass number. This is the total weight of that heavy core we just talked about, meaning the combined total count of protons plus neutrons.
So why does deeply understanding neutrons and protons actually matter to our world? Well, because once we found that neutral neutron, scientists realized they could intentionally shoot it into heavy nuclei like uranium to destabilize and split them apart. This single, massive discovery birthed the atomic age. It brought both the devastating reality of nuclear weapons and the immense potential of nuclear power. In India, a brilliant physicist and visionary named Dr. Homi J. Bhabha pioneered the peaceful use of this atomic energy. He established what is now BARC and the Dhruva reactor. Now, his life tragically ended in a mysterious plane crash, an event that has spawned several controversial geopolitical theories over the years, but his foundational work absolutely pushed humanity forward. Today, this continued atomic research leads directly to incredible, life-saving breakthroughs, from targeted cancer treatments and advanced superconductors to next-generation energy storage.
We started this explainer journey by looking at a simple brick wall, and we zoomed all the way down to a tiny, dense core that's surrounded by vast, empty space. I want to leave you with this final, profound thought to ponder. How is it that an invisible structure, something that is quite literally almost entirely made of empty space, holds the absolute power to both heal humanity and entirely destroy our world? The universe really is hidden in the microscopic. Keep exploring the cosmos within.